record this so that we can have it for those who missed it, or if you want to review it later. So what I wanted to do, I was kind of realizing over the weekend where we're at on the calendar, and we were kind of said we wanted to move to the Siemens at this point, but we wanted to try to touch everything. So we did 4 labs on the Micro800, and I think everyone did really well. Just kind of threw everybody in, you know, kind of threw everybody into the pool. No, you know, for the most part, I think with the exception of Calvin, no one had programmed the PLC before, at least not to my knowledge. So everybody kind of took it and did it. But what I wanted to kind of wrap up with here before we move on is maybe kind of tie up some of the loose ends, some of the pieces that maybe we didn't quite get to explain as well as we went, right? We just kind of threw out some scenarios, and we said, you know, kind of had to use a lot of your imagination, you know, say, hey, you got a start switch, you got a stop switch, you've got this and that type of IO, and just kind of make a program around it. So I understand not everybody has a good point of reference as to what all that really means and how that actually ties into the real world. So, you know, kind of going back before the storm, we spent a lot of time kind of lecturing on just the various pieces, right? We had the push buttons and the switches, and we talked about all the various control elements that you could face. So tonight we'll kind of try to once again kind of tie those two things together real quick, just to hopefully let it kind of solidify a little better in your head. And I think now it might, you know, some of it might start to click a little bit better now. You're kind of starting to see how this goes about. So let's start out with the wiring diagram, right? So this should look a little bit familiar. You know, we pulled it up on the board that night. So the very first lab you had was just to simply wire the Micro820, right? And we talked about how it was, you know, for the most part, it was very straightforward for our application, right? You had to bring power. Oops, let me see if I can get my pen. That's not nice. Pen will not work on the other side. Oh, there it is. Wonderful. All right, as I figure out where I am on the screen. All right, so we had the wire, you know, had to ride 24 volts, right? So we had a power supply, you know, 120 volt AC, and then that meant you had to, you know, come into those 2 terminals right there, right? And that was straightforward. And then on the inputs above, we had the, you know, the switches wiring up here to pins 3 or pin 2. So what I wanted to kind of talk about is, you know, what that really means and kind of the other labs, right? We didn't really, you know, we just kind of left it with that. You wired up one switch, you wired up the power, and away you went. So let me try to hopefully, and now realizing my drawing might be pretty bad here. Oh, okay, I think I see what's happening now. All right, so first lab was pretty straightforward, right? We had an input push button, right? We called it, I think, start. And we had a stop push button. And then we had 2 outputs. We had, I believe it was like a pump, like the motor starter. And then we had a pump running indicator, right? Okay, so so what that really meant was we had, you know, we would have had some kind of actual real push button, right? Some kind of a push button station, right? And we had those ones in the lab. You had kind of a start and a stop, perhaps. This could be on a panel or it could be on a little pedestal, right? And then what this actually meant was we had a contactor. And a contactor is basically a 3-pole relay that would go out and start the pump. The pump is assumed to be a three-phase motor. So the pump is attached to a motor, and that's really the motor is what we're going to energize here, right? We're going to turn on the motor. The LED was simply a light. So a good reference point, if you know, again, if it would be, think about a ceiling fan in your house, right? You have a ceiling fan, you have the ceiling fan has a motor, right? So you're going to energize the motor, makes the fan start turning. And if your ceiling fan has a light attached to it, well, then usually there's a second kind of pull chain for the light, right? So a little bit of a may or may not be the best analogy, but at least kind of understand there's a motor attached to the pump. Now, a ceiling fan situation, the motor spins the fan blades. Now, we saw that picture a second ago, which I kind of butchered when I didn't realize where I was drawing, right? So this is how they showed in the book. But what I want to show you is how this PLC drawing would actually look if we were drawing our own schematic, or if you had a schematic or a set of prints in the field, how would you look at, how would the drawing look? All right. So typically we don't orient it in the way that it's shown here in a schematic. Typically we orient it up and down. So we would actually, on a schematic, you would probably see it drawn in one of two ways. You'd either be kind of, since it's a brick PLC, it might all be shown as one box. If it's a PLC such as like the control logics where it's chassis based, you might see it as individual blocks. I'm going to kind of draw it as individual blocks right now, but know that this is essentially kind of one unit, right? And this side here on the left would be our inputs. And this side here on the right would be our outputs. So I'm just going to put in and out. And the point of this, or the reason for this, is because it kind of shows almost like the ladder diagram, where it's going to mimic the flow kind of into the PLC and then out of the PLC. So we're actually going to show a rail, a power rail, but this would actually be a real wire. So this would be the plus 24 volt DC. And then we would actually show a negative rail, and this would actually be the minus 24 volt DC. So this would be the real wires, plus and minus. Remember, you wired back up to your power supply. So that would be going back to your power source. Then we had our individual inputs on the PLC, and we had our individual outputs on the PLC. And going back a slide, right, we were referencing those as simply 1, 2, 3, 4, 1, 2, 3, 4. So I'll use that 1, 2, 3, 4, 5, 6. Now, being that the power was on 1 and 2, I'm going to start this side with 3, 3, 4, 5, 6, 7. All right. Also, I probably could have skipped 1 and 2 there, perhaps. But so 3 is where our first input was on the Micro800. So this start switch would be wired to pin 3. So we would actually come off this rail, go to the start switch, push button, and wire it to pin 3. Then we showed we had a second switch, or second push button, which was our stop. Now, we can choose to wire this to any input that we want. Logically, it just seems, like we would put it to pin 4, right? That's the very next input. It doesn't have to go to pin 4. It can go to any pin you want, as long as you keep track of it now in the program as to what it's actually wired to. So again, if I'm making my schematic, I'm going to label these devices on my schematic, because at some point, this would be a CAD file, of course, and not this horrible, chicken scratch diagram. But you'd have a CAD file that would show this neatly, and you'd be able to take this out to the panel and look at what's actually wired to the PLC. All right, now for the outputs, we kind of do the same thing, just a little bit opposite, right? So the outputs are always tied, where they're called sourcing, where the output is sending 24 volt out of the card, and then it's going to go to the negative rail to kind of complete the circuit. So we would actually come off this terminal 3, and we would indicate this as a coil, since it's a contactor. And then on pin 4, we would come off of here, and we would indicate this as an LED or a light, and we'd come to the rail. So this would be our, I'll call this pump, and I'll call this run for short, okay? And then if the LED, of course, will have a color, so we typically indicate the color inside this circle. So let's say it's a red light. So I'd put an R there to indicate that it's a red LED. All right, so that would have been the if we were going to really wire this up in a panel, this would have been, how we would have done it. Then the next piece, of course, was what you did in the program. You tied these physical devices to the actual memory spaces in the PLC. Because again, as you saw, when you push this push button, that sends the 24-volt DC to the terminal, or to the pin 3. And then the PLC had a little indicator right here that lit up, and it indicated that, okay, I've got power on pin 3. And that basically transitioned the memory space from a 0 to a 1, right? Again, it's in its Boolean, right? Computers, it's all, zeros and ones inside a computer and inside the PLC. So it was able to, it saw that transition from 0 volts to 24 volts, and it said, okay, go from off to on, which means go from 0 to 1. Right? And then we knew from the way how the Micro820 was, we know that that input was known as let's see, it was like what, IO.EM for embedded, DI00, right? And we knew that pin 2, or the second input, which was wired to terminal 4, was IO-EM-DI01, all right? And the same applied for the outputs, right? So we were able to tie in the outputs to their memory space, which was IO-EM-DO00. This is where it gets a little confusing, right? Because the O's and the zeros get a little hard to keep track of that. As you'll see tonight, when we go into the Siemens, they replace the O with a Q to make it less confusing. All right. So that was lab 2, basically, right? Because we just wanted to kind of, do a simple pump control situation. So just starting this pump took, kind of 4 things, right, in this situation. But that's not all of the story here, right? Because the pump contactor, which is basically this relay coil right here, is just energizing a coil. So we still have to interface that contactor to the motor, all right? So one of the piece of the industrial controls aspect here, so this would be, again, this is what the PLC is doing. And then inside of the, inside here is the magic of the program you wrote, right? But you still have to interface these external devices, perhaps with good old-fashioned wiring, okay? So start and stop push button, there's not much else to do there, right? You just wire a push button in the PLC. The run LED, the run indicator is pretty simple. You're just going to wire it, and when it gets power, it lights up. But the pump contactor still has to be wired to the pump or to the motor in order to make the pump turn. So let me just show you what that looks like real quick, because it's just important to kind of understand. So again, we have a contactor. So typically a contactor, right? We have this coil, and I'm going to draw it as kind of a device here, like that, right? So we have a coil, which would basically was going back to the PLC, right? So this was going back to the PLC. That's what the PLC was actually wired to, as a coil. But the contactor has 3 contacts on it. And this is used to go to a three-phase motor. Right, so we're basically going to have A phase, B phase, and C phase for three-phase motor. Now, let's say the motor is a 480 volt AC motor, and let's say it's got a particular horsepower to it, right? So when we're sizing a motor, there, we have to pick a motor that has enough horsepower to basically to spin the load or turn the load, right? In this case, it's a pump. So I don't know. I'm just taking a number. Let's just say it's a small pump. So let's just say it's a one horsepower motor. And the reason why that matters is because these contactors come in different sizes because there's a current draw. Okay, so horsepower can be related back to watts, basically, which of course watts can be related back to current. So we have to be able to, size our contactor to be able to handle the amount of current that motor is going to draw. If you put in a contactor that's too small, then that contactor is going to probably melt. Those contacts would melt together, most likely. And if you put a contactor in too large, well, that's not a problem. But then you probably, you spent more money than you had to, and you put a physically larger device in the panel than you had to. Nothing wrong with that, but it's just oversized. Okay. So being it's a 480 volt, 480 volt motor, right? This is 24 volt DC on the contactor coil, right? But these contacts themselves are 480 volts. So we would never bring 480 volts to the PLC itself. So if you're sitting here wondering why didn't we just bring that through the PLC? Again, two reasons. One, 480 volt AC, we would not do that to the PLC. And two, the current draw, because this could be 10, 12, 15 amps. It could be a considerable more current draw if it's an even bigger motor. And our PLC cards, those old transistors on those PLC cards, typically are rated for a half an amp. So you would blow that PLC incredibly quickly when you turn this motor on. So we have to use this external contactor to do it. All right, so just wanted to kind of show that piece of it. Of course, we would have our A, our B, and our C phase would come into the contactor. When this coil energizes, or when the PLC told it to turn on, these contacts close, and they're all kind of tied together, so they all close at the same time. And then here, we would actually come out of the contactor, and we would have a motor. And we typically kind of show the motor as just like a circle with an M on it if we're drawing a schematic. And then we would, of course, label this, right? Whatever it is, motor 1, we'd give it, the rating, 40 volt AC, 1 horsepower typically, and we would say 60 hertz, even though it's implied, anything in the United States is going to be 60 hertz, but it's still best to go ahead and define it when you're drawing this schematic so that we know that it's a 60 hertz system and spell it out. Okay, so from an electrical standpoint, this is what we need to do to make that pump turn. Now, there's a mechanical piece to this because the pump implies that it's pumping a fluid of some sort, right? So so there could be a physical pump that's attached to a piece of pipe that's going to be pumping some kind of fluid. Typically, as an electrical person, we're not going to really understand that aspect of it necessarily. We're not going to be involved in that aspect of it. So that's where a mechanical engineer might come into the project to size the pump properly and to design the piping that would take whatever the fluid is you're pumping through the system. If you're in a chemical plant, it could be pumping, hazardous chemicals, dangerous chemicals. Again, so that's not really something that's inside of our electrical wheelhouse typically. All right. So again, lab 2. Any questions on that? Just wanted to kind of help show that to you. So lab 3 was basically the same thing. We just said, hey, you got 3 motors now, and we kind of did a time sequence. So you basically take this and you kind of multiply it by 3. You've got 3 motors, you've got 3 contactors. We would have, power coming to each one. And in that situation, motor 1, 2, and 3, or pump 1, 2, and 3 could all be different size pumps. So the contactors could be all different sizes there. Like it could be and they go by like, they have like a size 1 contactor, size 2 contactor, size 3. So they kind of give them these kind of ratings. But in all cases, they would all have a 24-volt DC coil to activate or energize the contactor. Just that the contactor itself, the contacts themselves might be physically larger for the different pumps depending on the current draw of each individual motor. So if you're speccing out the rest of the system, you have to be able to know that, okay, my PLC is 24-volt DC control, therefore I need a contactor that has a 24-volt DC coil. But then you also need to know, what size contactor to purchase based on the motor size. Yep, a question out there? Oh, okay. All right, so going on to the last slide, the one we just did. I guess that was Thursday night, right? Today's Tuesday. So that one was a little different in that we didn't have a motor this time. Well, I guess we did have a motor, because we had the belt, the conveyor belt motor. In that case, the conveyor belt motors are going to probably be very small motors usually. If you're driving like a belt, like on a big grain elevator, if you've driven on River Road and you've gone under the grain elevator, you see those kind of belts that bring the grain out to the barges on the, or ships on the river. Those are going to be pretty large motors driving that belt. But if you're thinking about a conveyor belt that's like, inside the Amazon warehouse moving packages, those motors wouldn't necessarily be too large, wouldn't necessarily need to be that large. But in that case, we had several different inputs, right? We said we were going to have a photo eye sensor, so I'll call it photo eye 1. We had a photo eye 2. Then we had a start and a stop for the conveyor. And then of course we had the conveyor motor, and I don't remember everything we had, but probably had a light. I'm sure we had an indicator of some sort. Okay. So in this case, these photo eyes, and we talked about the photo eyes when we talked about discrete sensors. So the previous lab, was just simply contactors and start and stop push buttons. That's what we would call the discrete devices. But a discrete sensor would be, remember, we talked about contact and non-contact. So the start and stop push button would be a contact discrete device. You have to push it, physically push it. The photo eye would be a non-contact device, but it's still basically a contact closure. Once the sensor detects whatever it is it's supposed to be detecting, it closes a contact internally, and then it allows power to pass through, right? So for the photo eye, we had a photo eye kind of looks like this. You have a little kind of light sensor, and you have a kind of cord going off, right? It has a little light beam going out. And if anything like that, if the box breaks the light beam, then this basically, again, there's a set of contacts inside of there. The contacts close, and then it'll basically, there's 2 wires coming to the photo eye, right? So an in and an out, right? So that was in the contact closure, and that of course is what we would be wiring to the PLC, so that when the box comes by the photo eye, it detects it, the little contact closes, and then the PLC sees that as a high signal or a 24-volt signal, and therefore shows it as a 1 inside the PLC, right? So our wiring diagram would be exactly the same, right? We would have, we would show the inputs and the outputs, right? So we would have, Now in this case, we wouldn't draw this, we would either draw it one of two ways. We either draw it as a contact like that probably, or we could also show it as a switch maybe. We wouldn't show it as a push button, right? Remember, so we have these standard symbols, right? That's a push button symbol. Not drawn very well. And then remember if we had some other symbols, right? We had like a float switch. We had a flow switch. We had a pressure switch, and then we had a temperature switch, right? So it's important to understand and recognize these standard symbols. There's a I would say an agency, but there's an organization called ISA that kind of publishes standards, a lot of standards for the automation world. And these symbols come from an ISA standard. I think it's ISA 5-1. So all these schematic symbols are standard. So it's important, again, standardization, because no matter where you work, you can pick up a drawing and hopefully they're using standard symbols so everybody can recognize. Just like speaking English, we all can understand the so it's just a way to make sure we're all kind of using a common language, so to speak. So for the photo eye, this one could kind of be a little, I don't know if there's a standard symbol for a photo eye, so that one, I have to look that up actually, but it would probably be drawn as either a contact closure or potentially as a switch, possibly. Then again, 24 volts plus, right? So this is actually a 24 volt, power, right? So we're going to come to the, so 24 volts would come into the photo eye, right? 24 volts coming into the photo eye. And then when that contact closes, this goes to the PLC, right? So that's the wire, that's this wire here. And then that is that wire here, right? So that was 3, 4. And then we had our start and stop. So we would, draw that as a traditional push button. And of course, very important to label all these things. And then same thing on the outputs, right? We would come to our motor contactor. We would come to our LED indicator, right? And this would all be tied to the minus 24 volt DC. All right. Oops. So even though I said earlier, it's a conveyor system, it's a smaller motor, it's still going to have some kind of a contactor to turn it on. Now, that's assuming the motor is simply an on-off motor, right? So in the idea of the pump back there, there was really no variation. We were kind of treating it as a discrete device, right? It's either on or it's off. And that means that when we turn it on, it's at full speed. And when we turn it off, of course, it's stopped and there's no in between. Of course, in the industrial world, we have the ability to control the speed of the motor with what we call a drive. So, not all applications are simply turn the motor on. In many cases, in a simple application like a fan or a pump, it might actually be, just turn it on and it doesn't really matter the speed. But in situations where you're trying to do tight control of something, then you might be varying the speed of that pump, because you might need to vary the pressure or whatever, the fluid. So, and that's the case, you wouldn't be using a contactor in that situation, because again, contactor means that it's either on or off. Again, it's a discrete device. You'd use a drive, and a drive would allow you to vary the frequency and vary the speed of the motor. So in this case, the example we gave in the lab was, it's a conveyor belt, we just turn it on. So in this case, there was no variable speed to the belt. It was simply the belt runs, the belt isn't on. In the real world, you could very well see that might be a variable speed circumstance. But in this case, since I said it's a discrete device, there's a contactor, and if there's a contactor, then there's another device, just like we showed earlier, that would basically be the coil, And then if it's a 3-phase, then you have to have your 3 contacts, right? So just like before. Okay. So I don't know, hopefully this helps a little bit visualize, because again, you might be picking up a set of prints one day, and this is what the prints will look like. Again, CAD versus this hand drawing. But usually they orient it in this kind of left to right order, and drawn like this. Then usually also you would go ahead and kind of add all of them, right? So you would have all your inputs, and then if they aren't being used, then you basically just show them as unwired, right? That way you know that, okay, I'm using 4 inputs, but I still have another 5 available to me on this PLC, so I got 5 spare. And sometimes they might actually label it as spare like that. But at least you can visually know that this PLC's got some spare inputs, but you might need to use it one day. Same thing with outputs, right? So you would continue to show your outputs, and maybe label them spare as well. All right. Okay. Any questions on that? That clears it up a little bit better and didn't confuse it anymore. Let me now switch gears. So what's going to happen on Thursday? We are going to start on the Siemens S7-1200. So let me introduce that PLC a little bit to you. And I'm going to show you the TIA portal. And then we're going to pretty much do the same labs we've been doing with the Micro800 as far as the programming of those labs. Just that now it's going to be a little bit different, right? So the ladder logic's the same, but the way how Siemens references things and the way how Siemens, uses their instructions, it's just a little bit different, right? This is unfortunately where, things between different manufacturers are very similar, but yet also very different. So every manufacturer is just a little bit different in how they do things. So, but again, ladder logic or ladder diagram is a standard language or standard way of doing it. So the ladder part doesn't change any. The ladder logic that you've kind of been doing doesn't change. Just you'll see some of the the addressing we use and the way of those instruction blocks are going to be a little bit different look and feel than what you just learned in the Micro820. All right. So the Siemens S7-1200. This is kind of a, if you remember, we talked about micro, small, and large controllers. This would be what I would consider this a small controller. It's not a micro. I wouldn't call this a micro PLC. I would call it more of a small PLC, but it has some aspects that are similar to the Micro820 or to a brick or micro nano type PLC. And what is similar is you have the embedded IO. So underneath these little plastic, so this is actually the CPU module right here, CPU. So the CPU is kind of like the Micro820 in that it's all kind of contained. There's an Ethernet port underneath. There's embedded inputs and outputs on these terminals. But you have the ability to expand this guy, so you can keep adding IO modules to it. For what we have in the lab, they are going to be just a single controller by itself. There is no expansion IO on board. Now Siemens, this is just one of the many in their family of controllers. So the S7-1200 is kind of, but I think this is their terminology, is basic controller. And then they have more advanced controllers, such as the S7-1500, 300, and 400. And you can see they get kind of cool looking with the little displays on board and stuff. So we're not gonna mess with that because we just don't have that. But we have 14 of these S7-1200 workstations in the lab. All right, so just kind of understanding a little better, there are different models of the S7-1200. All right, so S7-1200 is the kind of overall product family, but now there are different classes of CPUs or different models of CPUs underneath the 1200. So there's the 1211C, 1212, 1214, the 15, and the 17. And basically, as you kind of move across the chart, you usually get to more and more, you get better performance or better, memory or whatever. Typically, when you see these type of spec charts, we happen to have the 1214C. This is what we have in the lab. So just like you're going to see a lot of similarities. Again, once we get into software, it's going to look almost identical to what what you're used to. So if you remember, when we went into CCW software, you had to choose your controller type, and there was the Micro810, there was the Micro820, the Micro830, the 840, I'm sorry, the 850, and the 870, right? So you had a couple of different ones to choose from. It's gonna be the same thing here. You're going to choose kind of the class, and then underneath the 1214C, there are actually 3 or 4 different catalog numbers or permutations. So you have to make sure you choose the right one, just like you did with the Micro820. So just from looking at the specs on this 1214C, we got 100 kilobytes of work user memory. We've got 4 megabytes of load memory, 10 kilobytes of retentive memory. We've got 14 inputs and 10 outputs, and 2 analog inputs built in. We got 1024 bytes of inputs, the I table. We've got 1024 bytes of outputs. That's our Q table. And we've got 8,192 bytes of bit memory. So that's just kind of internal. So we see this M here, that's just gonna be kind of internal memory. So just memory space that we can use inside the PLC that's not tied to any inputs or any outputs, physical inputs or outputs, just kind of a holding memory space for our program, to use inside of our program. And we can use up to 8 expansion modules. So again, these are the expansion modules. So we can put up to 8 of them, supports up to 8 of them on this particular model. And we know we can do a pretty decent amount of inputs because we have 1,024 bytes of just input memory space, and we have 1,024 bytes of output memory space. So if you think about it, the discrete input is a bit, right? Every discrete input is just a bit. It takes 8 bits to make a byte, right? So 1,024 bytes is a fairly large memory space for inputs. Now, when we get to the analogs, analogs take more space, right? They take a word length of space. So word is 16 bits. So, if we had analog inputs, which we're going to start talking about those here once we get into the Siemens labs, we're going to, we don't, it looks like a lot of memory at first for just nothing but push buttons and discrete devices, starts to kind of get chewed away if we had a lot of analogs in that system. But as overall, we have 1,024 bytes. So it just gives you an idea that, there is a cap to how many inputs and outputs we can really drive with this system. Okay, so just like we've been showing on the Micro820, the S7-1200 wiring diagram looks very similar to what we were just talking about. Since it is kind of the embedded I/O, meaning that the I/O is just on board the CPU, we're going to wire to the top and bottom. Now, first off, all the lab stations are pre-wired. They're all kind of come from a company that makes PLC training equipment. So there's nothing to wire here, which is why we did it in the 820, just because those were loose and it gave you the opportunity to kind of practice wiring a little bit. But everything else that we're going to be using is pre-wired. So but it looks very similar. So if you had to design this system, or if you had to do this, from scratch one day, it's very similar to what I just showed in the sketches, as well as what you did when you wired it. You've got power, right? So you always have a power supply you need to wire in. So this happens to be 24-volt power. It does give you 24-volt out in this one. So we have 24 volts that are required to come in, but then you can actually turn around and use that 24 volts that you kind of put into the system and send it out and wire to your IO. So you can actually just jump off of there to your IO, feed your IO with that 24 volt. And then on the top row, we have all of our inputs. So we do need to bring a negative to this terminal, and then we have our positive going out and being switched into all these inputs. We now have the analog input. Remember, so we had 2 analog inputs. So we actually have the few extra screws over here to wire your analog devices to the PLC. And on the bottom, we have our discrete outputs. So just like in the Micro820, the outputs are also on the bottom. And we're going to bring a 24-volt source in, and then we're going to kind of bring 24-volt out. And then every one of these little rectangles implies some sort of load. So that could have been the contactor, the coil for the contactor. This could be the light for the LED light, right? So they don't show them as circles, but these are basically loads. So this is what you're actually physically wiring to out of the PLC. So your loads, and all your loads, of course, we're going to be tied back to the DC negative to complete the circuit. So 24-volt DC out, as well as 24-volt DC in. All right. So where it starts to get a little different, and I guess in a way it's similar to what we've been playing with here, but you're going to have the kind of maybe a much, I guess what I'm trying to say here is that the Siemens system is going to be a little bit more sophisticated as far as programming organization. So we have this OB main, and then the OB main will be calling these function blocks, and then this function block can call additional function blocks or subroutines. So you kind of start with a main routine, and from there you'll call your subroutines in the system. What we just did with the Micro820 is you just create a program, and then you can create multiple programs if you want, but basically each program just executes. Here you can kind of control that program flow by calling the subroutines to operate. So the supported languages, just to kind of show, just like the Micro820, this was a ladder diagram, function block diagram, and then here's something new called structured control language. And then they also have in the 1500 the graph and statement list. So these are they're, again, this is just where there's I guess certain things just don't translate, because remember Siemens is a German-made PLC, so their terminology is just a little bit different than maybe what we're showing here in the Rockwell stuff. But ladder diagram, of course, is the same. Function block diagram is the same, but then these other three kind of have a little bit different nomenclature from what we were kind of shown before, but they're going to be very similar. Now, again, we're using the ladder just to keep life a little bit simple in this class, so we're going to be sticking with the ladder diagram. And in this case, they'd say LAD. Rockwell World, it was just LD. All right, so OBs, organization blocks, are the interface between the operating system and the user program. So don't worry about some of this definition yet, but just know that there's going to be these kind of, again, these kind of terms that when you're in the software, so they'll use like these little acronyms like OB and whatnot, FB. So just kind of just not to, just want to kind of define these things for you. So the organization blocks, or the OBs, are the interface between the operating system and the user program, and they're called by the operating system and control. For example, the startup behavior, the cyclic program processing, the interrupt control program processing, the error handling. So it's basically kind of like the main routine, basically. So basically, when the PLC first starts up, it's going to look at this OB to kind of know what to do, basically. All right. So in this case, the main one, OB1, is what executes first, and then it might call a bunch of subroutines. When that's done, it'll go down to the this main X, OB200. It might call a bunch of subroutines. Go down next. When that's done, it'll go down to this main Y, OB300. It might call a bunch of subroutines. And once it's finished with that, it's going to go back up to the top. Now, we're not necessarily going to create this every time. We'll probably just stick with just one main routine, but just know that it's sophisticated enough to where you can have multiple programs, and then again, each program calling multiple subroutines. That's good. Just know that, again, this will execute first. All of it has to go and do all this. Then it'll execute this and go and do all this, this and this, all that. So, your process time, your sweep time, can be impacted by how many of these, separate routines you have and how many calls to subroutines you might be trying to do there. Again, for our lab assignments, we're going to be writing just a few lines of code, but in a real world program, it could be much more sophisticated than just, what we're going to be doing in the lab. Now, here's where it starts to really get a little bit different from what you've been used to. So in the Micro820, we were doing, that embedded, right? So we had that underscore IO underscore EM for embedded, right? DI 00, whatnot. Here we're going to have a input memory table. We're going to have an output memory table, right? And we're going to have that M and the L and DB down at the bottom there. So we have some other additional memory tables that we can utilize inside the controller. So to access the input memory table, we're going to use %I. Okay, so the I would indicate that we want to read or look up out of the input table, and we use a % sign in front of that I to indicate that, hey, basically like a lookup, I guess, lookup I, and then you're going to give it an actual address in the memory table. And for the outputs, we're going to reference it as a Q. So we would say %Q and then the address. If we wanted to use the bit memory, the M memory space, we would use %M and then the address space. I don't think we're going to mess with the L and the DB memory space, but just know that there are some additional memory spaces that are available to you. So the way how to think about this now is it's going to be organized in kind of rows of data. We're going to have, and it's going to be byte aligned, meaning that we'll have, bytes, so 8 bits in a row, and then we'll move on down to the next byte. This is byte 0, byte 1, byte 2, byte 3, but this is bit 0. Now, whenever we're doing microprocessor, we typically, 0 is always the one on the right, and then we go from right to left, because this in the binary number is the least significant digit. And this over here in a binary string would be the most significant digit. So we typically read these tables from right to left, okay? So this is bit 0, this is bit 1, bit 2, 3, 4, 5, 6, 7 out of byte 0. All right, so we're going to be referencing these memory spaces based on the byte and the bit. Okay, so first we would give it an indicator. What's the memory area identifier? right? So this is, they show M in this example. So this would be the internal memory space, %M. And if I reference, I said, hey, give me, if I said %M 3.4, that means that I'm going to be looking for whatever is in this memory space right here. So here is bit 3, or I'm sorry, byte 3, byte 3, and bit 4. All right. So it's just a matter of keeping track of where you're putting things. Now, when you're using the internal memory space, that challenge gets, it's a little bit more of a challenge, because you can reference any of this memory space in here and use it. When you're using the input and output table, it's not quite as flexible, because my first input is going to be %I 0.0. Okay, my second input will be %I 0.1, and my third input would be 0.2. All right, so your inputs and your outputs will be kind of fixed in the table based on what position they are in the system, meaning that the inputs that are embedded on the CPU will be 0, will be byte 0 basically. Then if I added a second input card, if I add an expansion card, well, then that would probably mean, hey, I'm going to be looking at byte 0 now, or byte 1, sorry. So byte 1.0 might be the 8 inputs that are on the expansion card. All right. So again, once we get into programming, this might start to make a little more sense, or becomes a little more clear, but you're going to be thinking of now the memory spaces in this format. So being that now we have a table of memory available to us, we can actually kind of use that to our advantage a little bit, right? So if I just wanted to reference a bit by itself, I would do what we just said, right? I would say I 0.1. That would mean that, hey, go look at byte 0 and bit 1 and tell me, what it is, 0 or 1. And that just looks at the individual bit. But what if I wanted to take a chunk of data all at once? So I can now reference, that. So if I wanted to kind of look at the entire byte at once, I could say, go grab the 8 bits in a row, in byte 4. So here IB4 would mean that I would go take, if this was the I table, and that's byte 4, we'll go take all 8 of these bits. And so all 8 of these bits is basically a binary string, and that would, could be converted into an actual number, right? I could take that binary string and convert it back to a decimal number. So I could take that chunk of bits together as one as a one address, shall we say, okay? I can also do the same thing for word. A word length is 16 bits, okay? And then ID would be a double word. So if a word is 16, then a double word would mean 32 bits, 32 contiguous bits. I could reference that, all right? So if you're not that familiar with the computer terminology here, bits, bytes, words, double words. So again, 8 bits are a byte, 16 bits are a word, and then 32 bits would be a double word. All right, this is a little bit of a better picture, blown up picture of what the real piece of hardware looks like. Again, it looks very, to some extent, it looks very similar to what you're kind of used to. You've got the, the inputs are wired up top, the outputs are down bottom. Now, they say Profinet LAN. Basically, Profinet is Siemens kind of their kind of protocol that they use. But this is basically an Ethernet connection. So you're going to have a Cat5 cable, just like you plugged into the Micro820 you'll have a Cat5 cable plugged in to this Profinet port right here. Again, Profinet's just the protocol. Rockwell has a protocol too that you weren't even aware of it, but they have a protocol. It was Ethernet IP was the name of their protocol. So just because it's Ethernet doesn't mean that, I can't just plug a Siemens PLC onto a Rockwell network and expect those two things to talk. There is actually a protocol that runs on that Ethernet cable, and those protocols, are they're not proprietary. They are open protocols, but typically in the Siemens world, they're using their protocol, and Rockwell is going to use their protocol. And if you wanted to kind of bridge the gap between these two controllers, then you would have to use a protocol converter, or what we call a gateway, to basically interpret and interpret from one protocol to the next. It's no different than talking to someone from a foreign country. You might have to take your little Google translator out on your phone and interpret, right? It's kind of the same thing happens in the industrial world with the protocols. All right, so I like this picture. I put it here just because it shows you that, it kind of reiterates kind of what I was shown a minute ago when I was trying to hand sketch these things, right? So inputs on the left, outputs on the right. They just kind of drew them as little squares and diamonds, but it's kind of the same thing. So that's, so push button 1 is wired to, it's going to be in memory space I0.0. Push button 2 is an I0.1. This will become relevant to you because when you start programming and I say, hey, I want you to use push button 3, well, then you're going to be basically referencing I0.2 in the memory space in order to get the signal from that push button 3, right? They couldn't be nice and say, PB0, PB1, PB2. They use normal numbering for the push buttons, but yet in the PLC, in terms of PLC, it is of course computer, computer numbering 0.0, 0.1. Same thing on the outputs. So there's a bunch of LEDs that'll be, a bunch of lights that are wired on the train stations, DO0, DO1, down to DO7, that you can use in your programming labs. All right, so how does this look different, or how does this, this part? So again, the ladder diagram is identical, right? So here's our good old tried and true latch circuit, right? We got a start push button, we got a stop push button, we've got some kind of running, such as a motor or whatever, and then we're latching it on itself. The difference is in the Micro820, we had to basically say, IOEM DI 00, right? IOEM DI 01, IOEM DO 00, right? But now we're going to be using those memory spaces we just talked about a moment ago. So now we're going to tie in the start push button is going to be %I 0.0. The stop push button was %I 0.1. And then our first output is %Q 0.0. All right. So that's how we're going to address these things. All right, so as we go along, we will do timers and counters just like we just did in the PLC, in the Micro820, just to show you that they, every PLC kind of has those same instructions, just that they're just different, a little bit different in how you go about using them. So in this case, this is the timer on, or the on delay timer. So you have your input. This is basically what's going to trigger the timer. Your PT is basically the time, what is the time value for the timer? Like what is the length of time to time out? The Q is the output of the timer. So whenever the timer is done, it'll kind of send out on the Q. And the ET stands for elapsed time. So that is similar to, of course, to what the Micro820 had. But it just looks a little different. It has a little different terminology there perhaps, but essentially it behaves in the exact same way. When you trigger the timer, it'll start timing based on whatever this preset, the P typically stands for preset, preset tag, right? So preset tag, whatever that is. And then you can look at your timer with the elapsed time. And then when it's done, it'll energize the cue, and that can go out and drop a contact or a coil, or should go out to a coil, I should say. All right. These timing diagrams, if you see something like this, they're just kind of trying to show you, what happens, right? So here's your in signal, right? So when your in signal triggers high, right? So this is like low. This means 0, right? And then when it triggers high to a 1, then that means that our elapsed time starts timing, okay? Or so we start timing, and here's the time, the preset tag. So let's just say it's a 10-second timer. All right. So, okay, we start counting to 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When we get to 10, well, we're basically at the top, right? We got to the preset, right? We're not going to keep going, and the cue, of course, now transitions to a high, right? So we got the input trigger, we count the 10, right? The cue is not on, of course, in that transition time. And then once it does make the 10, the cue triggers to a high. Now, when the input goes back to 0, well, then this goes to 0 and the output goes to 0. So here everything is 0, 0, 0. And what they're trying to show in this one is that, okay, the input turned on, the timer starts timing. It didn't quite get to, right? Then we lost our trigger signal and went back to 0. That meant that this went down. We never got the output on, right? We kind of saw that in the labs if you were messing around the timer enough. And then here, only when the trigger stayed on for the full 10 seconds did we finally get the output to turn on, okay? But the timing diagram, very common. You might see things like that, but that's kind of how you would read that and decipher that. At first, it looks very confusing, but you're looking at how, how everything trigger, everything will trigger off of the input. And then this is how everything else kind of behaves based on that trigger. See how the off delay timer. So I won't go through all that timing again, but we know the off delay timer worked where when you de-energize the timer, that's when it started the time. And that's kind of what happens if you look at the timing diagram here, right? We're high. When we go to low, that's when the preset, it starts, or the elapsed time starts timing. And then the cue is already on. And then once we finally get there, that's when the cue actually turns off. So it just kind of works in opposite to the on delay. And there's an on delay retentive timer. So we were using, so I don't think we didn't talk about this timer, I think in the Micro820, but there is a retentive timer, meaning that if for some reason I lost my trigger along the way, the timer would actually hold its value. It's just like a pause. It's no different than hitting pause on the on your stopwatch or something. And then when you kind of took it off a pause, it just continued to time. And these are very handy because again, there could be situations in your control where you don't want to have to start the timer all over again. We were using simple 10-second timers just because it was convenient and easy, right? 10 seconds. But let's say you had like an hour timer, right? Or think about, anytime you launch a rocket into space, there's always a countdown timer, right? And you're always hold and pause at various points, right? So you wouldn't start the clock all over again back to, an hour, right? So you want to just pause along the way, but then keep your timer going. When you need to unpause, then you'd use this retentive timer, as it's called. All right, counters. So we were just messing with counters on Thursday night. There's a CTU, and of course there's a CTD. So count up counter. So it's going to work very similar, right? We'll have a trigger in the CU. We'll have an R for reset. We have P for the preset value, C for the count value, and then Q for, whenever the counter gets, to its preset value, your Q will turn on. So you can kind of see that, again, there's a timing diagram or operation for that too. So this actually looks very similar to what we just messed with the Micro820. So very similar, even I think very similar in the terminology here, perhaps. There's a CTD for countdown. Now, when we get into analogs, and we're going to get to there probably next week because we haven't done analogs yet, we will have to talk about scaling and normalizing the analogs. And before we get there, I won't do that tonight, but we'll talk a little bit about what that means before we get to that lab. So, but there's a block in the program that we can use to basically scale. And scaling means that we have to take the, once the value of the analog signal comes into the PLC, it's in it's in a byte or actually word. It's in a word format, and we'll have to convert that to an engineering unit. We'll call that, because that number that it comes in as, isn't a usable number. It's going to be based on 2 to the 15th power, or so you have to kind of convert it back to an engineering unit. For instance, if it's in PSI, you need to put into whatever the PSI scaling is for that transmitter. So we'll talk a little more about in detail that before we do that the lab. Okay, and on Canvas, there's a whole bunch of Siemens references out there. So if you'd like to kind of, study up a little bit, there's the user manual, there's this easy book, there's a lot of documentation, just from Siemens themselves. You can kind of look through that book a little bit before you go. But now we will once again tempt fate with technology on a live Zoom, and I'm going to open up the software that you will be using on the in the next lab. So Rockwell Micro820 was called Connected Components Workbench, or CCW. I like to have these little acronyms. The Siemens uses what's called the totally integrated automation, or TIA portal. So totally integrated automation portal, or TIA portal for short. So even though it's a different look and feel, it's essentially the same thing that you've just been doing with the CCW software. So of course we can open an existing project, we can create a new project, you can do a migrate. You can also do a welcome tour. So if you want to kind of, thumb through here, it'll kind of show you around the software a bit. We're going to go create new project. Have a project name, path, default, the version. We're using 15.1 version software. And if you want to put a comment in here, you can do that. And we'll say create. So this will take a moment. All right, so now that we have that, we'll get to this part here where it says, hey, project 2 is open successfully, please select the next steps. So the next steps we need to do is, and it kind of shows you the workflow, configure a device, then write the program. And then if there's some additional pieces here like motion or visualization, which we will not be doing, we can do those here if we need to. But just like, again, just like we were used to in CCW, we have to tell it, well, what is it we're going to program? What are we going to do? So we want to do a configure a device. And we do configure a device, we will come to add new device. And when we come to add new device, you'll see that we have several options. We have controllers, we have HMIs, we have PC systems. So just like CCW software, you had multiple things you could have chosen there, right? But we're going to stick with controllers. And as you can see, we have a lot of options, right? We got the 1200 to 1500 to 300, 400, right? We are using the S7-1200. So if I expand that, and then we say CPU, expand that, then you see, whoa, we got a lot of options here, a lot of options, right? They got the 11Cs, the 12Cs, the 14s, 15s, right? So just like we showed in that chart. But then to make life even a little more complicated, each one of these has multiple options too, right? So we got the 1211C AC DC relay, RLY stands for relay. We've got the 1211C DC DC DC. So this basically talks about the different types of models. So that's AC, we mean it's an AC power supply. DC means it's DC input, and the third is the RLY, means it's the type of output. So a DC, DC, DC would mean a DC powered, DC inputs, and DC outputs. So that's how we can kind of decipher that real quick. In the lab, we're going to be using the 1214C, and we're going to have the DC, DC, DC model. So we have to expand that. And you see now we have 3 additional choices at our, here for us. So basically different models. So everything's the same except for these middle characters here. So we have an AE30, an AG31, and an AG40. So this is where I will tell you that when you sit down at your training station, you'll have to look at your unit and it'll tell you. Unfortunately, we have a bit of a mix in the lab. We have some stations that are AG31 and some stations that are AG40. If you pick the wrong one, when it comes time to download your program, it's going to give you an error or a fault. So you'll have to go back and fix this. So it's just, I'll remind everybody Thursday night, but look at your station, it'll be marked, and make sure you pick the, pick the unit that you actually have at your station. So for tonight, I'll just pick the AG40. So just like before, this looks kind of very familiar to the CCW, right? I just chose it. It kind of puts a little picture of what it looks like, gives us some descriptions on it. I still have to choose add, and I'll choose add. This will kind of complete building the project or the device. Let this kind of go here for a moment. All right. So again, they are very similar in the look and feel. This looks very similar to what happens when you first open up CCW. It kind of gave you a little visual depiction of the PLC you had. So this is just a nice little visual indication that, yes, this is what my PLC looks like. If it was like longer or something, that you would know that maybe this wasn't, I didn't pick the right one. So just a quick little visual. Just like in the CCW software, you have all your properties down here. General, again, so remember Profinet here, Profinet will mean the same thing as Ethernet. It's just their protocol. So if I had to change my IP address on this PLC, I would actually come under Profinet and an Ethernet IP or Ethernet addresses, and then I can type in my IP address right here. Each station, so now we're going to move into the world where the PLC will actually have an IP address that is defined and static. It's not going to be fluctuating every time like it was with the Micro820 PLC. So every station will also be labeled as the IP address. So when you create a new project, it's going to probably have a default IP address that it just picked. For me, it picked this. So it will be important to make sure that you put in the IP address here in the project that matches what is on the station itself. That way you can get connected to your controller. We'll remind everybody about that on Thursday night too, but just note we'll have to actually type in an IP address this time. We didn't really do that with the Micro800. So the rest of the configurations kind of just all hiding down here. We can look at our our inputs, we can look at our analogs, analog inputs. We have 2 analog inputs. So we will, when we get to the analog, we'll probably have to come here and mess with this a little bit. So we'll do a little bit more configuration than we typically have been doing with the Micro820 in this PLC. A little bit, but not a lot. Then we can kind of see here a very similar looking kind of IO table. They call it device overview. And this is just kind of showing our kind of our addresses. So we're using DI14, and we're using Q addresses 0 to 1, Q address 0 to 1. Our analog is using 64 through 67. So this is just letting us know how we're going to actually reference some memory spaces, right? So we can actually change this if we wanted to. So, and it tells you what your valid range is. So if we don't like, if I don't want my analogs to be between %I, 64 and 67, then I can actually adjust that in this chart. So at this point, the only other thing you need to really do is, for our first labs, is we're going to go to program blocks. So, so you see we have probably have a lot more kind of options here underneath this, the tree, the navigation tree. But we only really need to worry about the device configuration, which is kind of where we are now, and the program blocks for programming. Now we have the main OB1. So kind of what we was trying to show in the slides earlier, we have the main routine OB1. So I can double click on main. And the main routine, as its name implies, is, for lack of anything better, is the main routine, meaning that that is the routine that will always execute first. Okay, so for our simple lab programming exercises, we're just going to go right into the main and add our code. If I wanted to make subroutines or additional programs, well, then I can say add a new block, and then we can add new blocks. If I did that, because I need to double click. If I double click on that, I give it a block name, and then what type of block is it going to be? Is it an organizational block? Is it a function block? Is it a function? Is it a data block? And then I choose what language do I want it to be: ladder, function, block, or SCL, right? So again, we don't need to create a new block. In this case, we already had the main created for us. And then you will basically create logic, just like you've been doing with the CCW. You got your elements here. So I got my normally open contact, my normally closed contact, and I got a coil. So I can bring my normally open contact down here. I can bring my my coil right there. Okay. And now I was able to kind of build this without addressing anything, but it has a red and it has question marks. So at this point, I would double click, and there's going to be kind of no pull down in this case. So what I would actually need to do is I'm going to address it just like we've been talking. I'm going to put a %I 0.0, and that will tie that contact in the program to the first input memory space. And then over here on the coil, I'm going to go %Q 0.0. And that'll tie the, and I hit enter, and that'll tie the coil to the output memory space. Now notice how it just started creating these tag 1, tag 2 terminology. It just kind of automatically did that. So the other thing we might do here is you go to your PLC tags, and we can say show all tags. And then here's tag 1 and there's tag 2. And we see that it is a Boolean, and it is addressed to the %i 0.0 and %q 0.0. So if I wanted to change this, I can do it right here. So I can make that my start, and I can make this my motor, right? And if I go back to the program, that should have updated. All right. So pretty much the same, little different, some nuances to it that we'll have to just, you'll have to just kind of, learn. There's all the timer instructions and everything, counter instructions are all over here, right? So if I wanted to add timers and counters, I can find them over here and basically drag them over onto the rung, right? And then give it a name and hit OK. Just took the default in this case, right? So this is what we'll play with on Thursday night. Of course, the next trick is getting connected and downloading to it. That's something I can't do right now just because I don't have a system to connect to. So we'll kind of go there on Thursday night. But basically, it's going to be going online, and it's going to be very similar to the first time that you connected to the Micro820. You had to give it a path. It has to know the path. So you have to, it'll allow you to kind of, so Siemens software has a similar tool that will kind of check all the things that are connected to the computer, and then it'll find your PLC hopefully, and then you can kind of highlight it and then choose to connect. And once you do connect, it'll ask you, do you want to download the program? Just like, this Micro820, you'll say yes. Do you want to run the program? You say yes. And then you'll be able to monitor the code executing just like you did in the Micro820. So, so I think the transition, shouldn't be that hard, but we'll, again, we'll actually do it for real on Thursday night. And I think that's pretty much all I want to kind of cover tonight. Probably a little bit longer than I had intended to, but probably why I was figured we do Zoom too, is I figured it'd be a little bit short and sweet versus having to make you come out on campus. So I will open up to any questions. Also, we'll make sure I get everybody here accounted for. So don't drop off yet. Let me just check everybody in. Let's see, Kirby, Kia, I got Edward, where are you? Let's see, Brent. All right, I think I got everybody accounted for. So no questions. Now, also note that in the past we've had the CCW software was free. You could download it and you could run it unlicensed, and you were able to kind of play around with it if you wanted to with the little simulator. Unfortunately, the Siemens software does not offer that ability. There is a license required. Now, it will work for a short period of time, like for, I guess, a couple of days or so in demo mode. So if you really are interested in installing this software on your computer, you can do that, and it'll work for at least some period of time, but it will, over a period of time, stop working whenever its trial mode is done. So if you want that, let me know. And we have the disk, and we have the disks in in the class. You can't keep the disks, like the CCW software, you can keep those disks if you want. These you can't, so just basically use it, install it, and then bring it back. You can also download it from Siemens website, but it's a treacherous path to figure that out on your own. So it's easier to use the disk if you got a drive on your laptop. All right. So point being, we'll have to be in the lab Thursday night to do these. Can't do these remote. All right. And if that's no questions, we'll wrap it up. Appreciate everybody joining, and we'll see everybody Thursday night.
Thank you.
You have a good one.
Okay, good
Y'all too.
night.
Thanks.
All right, thank you.